Welcome, everyone, and thanks for joining us for the Appalachian Energy Summit webinar series. My name is Lee Ball, and I am the Chief Sustainability Officer at Appalachian State University, and I will be your host today. The title of today's webinar is Practical Optimization, When to Use ML or Machine Learning and When to Keep It Simple. The Appalachian Energy Summit is an effort to convene energy, sustainability, and transportation, waste, and other professionals across the higher education, local government, and industry landscape. The goal is to exchange knowledge, best practice, and essentially learn from each other. The Appalachian Energy Summit webinar series is an effort to continue some of our efforts as a result of the COVID pandemic. Our last two webinars in the series include sustainability and energy initiatives in local government, which is happening on October the 15th, where we'll have a special guest, Amanda Weaver from the city of Asheville. And on Thursday, October 22nd, Principles of Integrated Project Delivery, where we'll have Howard Ashcraft, a partner of Hanson Bridget LLP. Today, we have presenting Travis Smith, who's a principal at Smith Engineering. Mr. Smith is an engineer with expertise in the design and optimization of college and university, healthcare, pharmaceutical, commercial, and government facilities with a focus on central utilities. He has an extensive amount of experience in these areas, and we're extremely lucky to have and proud to have Travis here with us today. Travis, thanks for joining us.
Hi, how are you doing today?
So I wanted to let you and everyone know that the attendees came in muted. We're going to have a question and answer session that is going to be at the end of your comments. And so if anyone wants to ask Travis a question during the webinar, then please put them in the Q&A that is kind of on the bottom right of the Zoom screen. We'll be taking those questions at the end. If you put them in the chat, we'll be paying attention to that as well, but try to get them into the Q&A. This is also being recorded, so hopefully we'll be able to repost this again for everyone's viewing pleasure in the future. So Travis, welcome and thanks for being here today.
Okay, great. I'm going to share my screen and start my presentation. Make sure everybody can see it. Maybe somebody can give me some feedback that they can see the screen here. Good. Are you able to see the presentation, or are you seeing a Zoom screen?
We see the presentation.
Okay, perfect. Thank you. Okay, so I'm going to give a little background about ourselves, just to set some kind of precedent for what we do and some background, but I'm going to keep it pretty short because I want to get into the meat of the presentation here. So we really have two companies. One's really an analytics company, that's BEP, and then Smith Engineering is more traditional consulting engineering services. All of our services are around facilities teams. So we don't do the traditional new construction projects. It's all to help facilities save energy and to run optimally. Just to establish some credibility, we've done over 1,000 tons of chilled water, as was mentioned, but the majority of our focus has been in complex plants. So larger plants, especially with added complexities of thermal energy storage, steam turbine chillers, cogeneration, or multiple hydraulically interconnected plants, we extend through the distribution system and then into the utilization of that energy on the campus side, or so the air handling units, basically. So I want to start off with our philosophy. So this is not a hard, fast, written in stone, this is how you have to do it. This is how, over the past 10, 15 years, we've kind of seen what works well. So I'm sharing our experience, but that doesn't mean that there's a right or wrong way. So the philosophy has these bullet points that I'm going to run through and give some examples. We believe in leveraging existing assets as much as possible. So maximize the investment that's already been made. A lot of times the chiller you have, the coil you have, the things that you have are definitely are cheaper than the things that you don't have. So a lot of times we'll go in and we'll see for example, Carrier 17DA from the 1970s. That's an amazing industrial machine. You can buy that machine today. It's going to be maybe $7 million. It's substantially more expensive than a commercial grade piece of equipment. We would recommend, upgrading that thing, improving the controls on it, and all that embodied carbon. There's just so many reasons that makes sense to leverage that asset. The next point, maybe one of the most important points here, is training. We're at this place in the progression of buildings where there's a heavy integration between human and machine here, right? So there's still a heavy involvement of human activity, and those humans need to be trained, or complex logic and optimization is going to fail. And we've failed. So we've failed hard, and we've learned that training has to be integrated in the process. We actually will not engage in a project if we can't do training. And the training starts with training before. That training builds trust. We have to build trust with the operations team. So the training builds trust that we know what we're doing. The training also allows the operations team to feel part of the team, and it also allows them to sustain the optimization. If they understand how it works, why it works, it's going to sustain. And then the final selfish reason is we get a bunch of tribal knowledge within that training before we implement the project that helps the project become more successful. Domain knowledge is paramount. You can't just drive the car by the site, throw some optimization logic out the window, hit the gas, and it's going to work. You have to really understand these pieces of equipment. Each piece of equipment responds differently. You can damage different pieces of equipment differently, and you really, really, really have to understand this stuff if you start controlling it. Optimization in the controller. So we believe that if it's simple machine control, it should be done within the BAS controller for multiple reasons. There shouldn't be costs into perpetuity on simple logic. You should own it. And at the end of the day, you're going to have a local relationship with a controls tech that's going to need to be able to get into that controller and modify this stuff on the fly if there's an emergency or something like that. And that leads me to the next one. The code needs to be simple and reliable. In the early days, we made science projects, right? We made it extremely complex. And what would happen is you walk away and you're going to have a controls tech that goes in there and looks at it. And if it's a science project or PhD level, he or she's going to say, hey, I'm going to just have to comment and abandon all of this stuff because we got to get this plant up and running. We got to get this classroom going, this lab going. We need to be able to maintain that logic. So some things require complicated. I'm not saying that certain things don't, but if you can write it in 2 lines of code, 700 lines of code is too much. And I'm even willing to give up 5% of the potential savings to go from 700 lines of code to 2 lines of code, because I know it's going to be sustained. What good is savings and improvement if it's not sustained? And what happens is if an instrument fails, I need to be able to drive a truck into this code and it still function. So you need to go through all those what if scenarios. And then there are complex solutions that are required, such as economic dispatch, load predictions, real-time M&V. I'll give an example of real-time hydraulic modeling. That stuff is too complicated to reside within the BAS controller. That stuff has to live in an analytics engine. One of our preferred analytics engine is Pi, but we're agnostic. There's a lot of analytics engines out there that, as long as it's customizable by your team, that is one thing that we're really adamant about. So I'm gonna get into so here's some examples of these strategies. I want to give some examples of strategies that on the chill water plant side that should be done in the controller, the building side that should be done in the controller, and then some examples of things that should be done in an analytics engine. So simple things such as pump staging, tower staging, chiller staging, chilled water supply temperature reset, chilled water chilled water DP reset, condenser water supply temperature reset. Some of these could be done in an overlay optimization platform, but they can also be done within the controller. On the BAS side, static reset, supply air temperature reset. This can get very complicated if you have two different fuel sources at the plant level, and then you're trying to maximize or minimize for either carbon reduction or dollar, minimizing costs. So this one can have a complex component to it, and I'll give an example of that. But optimizing economizer, that can be done within the controller very easily. Some examples of things that should be done in an analytics platform are TES dispatch. Thermal storage dispatch gets very complex and is too complicated for the controller to be done properly. Obviously, the thermal storage control can be done within the controller, but when to charge and when to discharge, when to run a steam turbine chiller, when to maximize the output of the gas turbine, when to minimize the output of the gas turbine. These are things that require a load prediction to be done optimally, and a good load prediction requires complex analytics. Some other example, demand response, measurement and verification. To do that right on a real-time basis needs an analytics platform. I probably have too many slides for the time given, so I'm going to move pretty fast here. I'm going to start with some of the optimization strategies in the controller as examples. The backdrop we have here is Princeton University, their thermal storage tank here. This stack is the exhaust of the LM1600 gas turbine. And then in the foreground is the main chilled water plant. In the background is the thermal storage plant. And they have an offsite geothermal plant that it's in construction right now. So I'm going to talk about, my first example is pump staging. So this is a pretty simple, this is a problem that is solved pretty easily from a keep it running perspective, but in very rare cases is it done optimally. So I have some examples of some pump curves here for Princeton. They have on the thermal storage plant, they have 400 horsepower chilled water distribution pumps. The pumps are oversized on head, which is typically what's done because you want to be able to plan for future growth of the campus. And you also are nervous because you calculated head and you don't want to install a pump that doesn't have enough. So you always kind of oversize it as a consulting engineer. But with that being the case, well, let's covering the horsepower equation. Horsepower is flow times head divided by a constant times the pumping efficiency. So really three things drive horsepower: the flow, the differential pressure that I have to generate, and then the pump efficiency. So looking at this example, here's my 4 chilled water pumps kind of represented in a little bit different way. So this is the efficiency. We have head and flow of the pumps. This is a snapshot, so one instant, just to drive home the example. They're running pump 1, pump 2, and pump 3, and pump 4 is off. They're sending out 7,863 GPM to campus at 135 feet of head. This is the operating point. So they're on VFDs. We're all happy. The VFDs turned down. It's maybe at 70% speed. I don't have speed on here, but it's a little bit irrelevant for this example. So we're all happy, but we don't have any idea what the pumping efficiency is because we don't have those analytics brought in. And that's a simple formula. I just take that previous formula, solve for efficiency, and put that in my controller, right? But I'm running at 56% efficiency, which is not good. Total kW consumption is 375. So the counterintuitive solution at this example is to turn on the 4th pump. So I went from 2,600 GPM per pump down to 2,000 GPM per pump roughly, or 1965 GPM. Now I'm running 4 pumps. The pump is running at its best efficiency point, or pretty close to its best efficiency point now. It's at 76% efficient, and the kW reduction is 115 kW. So another important thing is to remember the first law of thermodynamics. That heat doesn't just disappear. That heat came out of the chilled water system. So when I was wasting that 115 kW, we have an open drive motor, so 96% of that kW is going into the chilled water system. So if I multiply that out, 3412 divided by 12,000, that is 31 tons of chilled water that I took off the chilled water plant. So I'm paying the utility to waste electricity, and then I'm putting that heat into the chilled water, and I'm paying the utility a second time to reject it out into the cooling tower. And the solution was very simple. I utilized the existing assets that I have. We didn't do training, so let's see what happened when we didn't do training. So here's how it ran before, and then we implemented this new logic, and then it was running great, but then all of a sudden the power went back up. The power went back up because the night shift operator says, why the heck am I running 4 pumps when I normally run 2? So we went back to 2, power went up. We really learned the hard lesson and said, hey, we got to train these guys ahead of time. And then, you know, we did the training, we did some commissioning, we gave them KPIs. It's really important that they have the KPIs that the guy at the night shift can say, hey, I don't know if I trust this guy. Let me try it out. Let me go to 2 pumps. So sure enough, KW went back up. Let me turn the pumps off or turn it back on. And we have the sustained savings. So what's really important here, there's an important takeaway of a lot of people see this presentation, they say, okay, if I have pumps in parallel, I should turn all those pumps on. That's definitely not the right answer. So if I turn on the 4th pump, let's say I had a 5th pump and a 6th pump in this scenario, it's going to keep moving to the left of the curve, and I'm going to eventually get to another bad spot on the curve. So this is how simple the logic is that can accomplish this. This is kind of a representation of the 4 pumps running. It's basically pretty pictures to show you guys. But now we're going to constantly, now I have more run hours on my pumps and I'm going to damage my pumps. No, the exact opposite is the case. Almost in all cases in energy systems, consuming extra energy means I'm running inefficiently. Where is that power going? Well, in the pump's case, pump operation to the right or the left of the best efficiency point, the impeller is subject to axial and radial forces. The level of axial and radial forces depends on the pressure within the casing. So basically, I'm paying the utility to jam this shaft, this impeller shaft, into my bearings and damage my bearings on the pump. So yes, they're going to have more run hours, but they're going to last much longer because running off of BP, spending that energy to damage the pump is going to cause premature failure much earlier than running the pumps for more hours. And also the bearing life is a function of speed, and the pump's running at a lower speed. So the pump is really happy right now. It's going to last a lot longer, and we're saving energy. So that's a pump example. I know I went through it pretty quick, but I think you get the concept. And there's a lot of savings that can be done there. And it's a fun one to play with. You know, go out to your pumps, make sure you're doing the same conditions. The important thing is, you know, if you turn the 4th pump on, did your flow increase or did your head change? Turn on the 4th pump, get it back to the exact same conditions. So you've normalized your little experiment, and then see, did the power go up or did the power go down? If the power went up, you moved it too far to the left. And you can look at the pump curve beforehand before you even try that experiment. Okay. So we're going to go on to tower staging. I'm trying to give examples of things that are really, really simple here that can have a huge impact. So on tower staging, let's say I have 3 cooling tower cells in this example, and I'm running 1 cell. So what does a tower do? It's going to it wants to evaporate water to reject heat. The majority of its heat transfer is due to evaporation. So it needs to evaporate water. And evaporation is a function of heat transfer. That's why it's equipped with a film fill to spread out that water. So I'm going to give an example here where we're running 1 tower at 400,000 CFM. We turn on 2 towers at the exact same operating conditions, and that means I can spread the 200 CFM out over the 2 towers. The cooling tower is the single piece of equipment in HVAC that actually follows affinity law. At 0 flow, I have 0 differential pressure, which has 0 horsepower, if it could go down to a minimum speed of 0, which it can't. But all other systems, I'm holding a minimum differential pressure or some type of set point. So there's never a minimum There's never a 0, 0 XY intercept, whereas this has a 0, 0 XY intercept, right? So it follows affinity law very well, the cooling tower. So running these two fans, I'm at 12.5 horsepower total. The trick is I've doubled the heat transfer surface area. So that's a somewhat a linear approach, a linear reduction in approach temperature. So now I'm making 81.5 degree Fahrenheit condenser water with a substantial reduction in fan power. So now I have a choice to make. Do I want to increase the horsepower back up and drive this water even colder? Or do I want to drive this set point back up? And that's the next complicated choice that I have to make. But in general, I just saved a lot of energy because I saved a lot of horsepower at the cooling tower, and I'm going to save a lot of power at the chiller because I have definitively dropped the lift on the chiller, which is going to reduce the power consumption of the chiller. So the simple optimization answer here is run as many towers as you can before you start getting uneven flow distribution through the fill. And from our empirical data, you see the channeling here, the theoretical. So I'm not getting, think about that sprinkler in the cooling tower. It doesn't have enough pressure because I'm spreading the flow out too much. So it's not spraying and fully wetting the fill. So our empirical data, or the theoretical evidence says that there's less pressure drop where the water is not at, and the air is going to pass through there and not pass where the water is. I get ineffective heat transfer. Our empirical data says that's actually not a big player. But what does happen is when I'm not fully wetting the fill, I'm splashing water on the fill. It's drying out. I'm splashing water. It's drying out. So I'm depositing minerals on the fill, and I'm going to prematurely destroy the fill. Obviously, taking that plastic to the dump and buying new plastic, all the embodied carbons there, not to mention the substantial cost. I'm gonna negate a lot of the gains that I got. So the simple solution is just use as much heat transfer as you possibly can for the given condition without channeling. It's that simple. We don't need to pay a black box into perpetuity to make that decision for us. So let's give the example in a commercial office building, which you guys don't run, where or a case where maybe there's not much impact to savings on the chiller. Let's say I have a pre-1999 carrier train CVHE or CVHF. It didn't have a refrigerant pump to cool the motor. It didn't have effective oil return technology. So I can't run really cold condenser water to that chiller. So what I want to do is then I might want to bring the condenser water temperature back up. 85 is way too high, but I'm going to take the savings at the cooling tower and not take the savings at the chiller. So the relationship between the cooling tower's performance, the condenser water pump's performance, and the chiller's performance is a pretty simple problem to solve on an optimization. It's a very simple optimization problem. You go to Stanford, you give this optimization problem to these guys, they're like, you kidding? Is there more to this? You know? So this is a pretty straightforward optimization problem to solve and can be implemented in the controller or could be implemented in a analytics platform. I'm gonna skip that slide. Okay, so I know maybe to some of the audience, those felt like complicated problems, but we're gonna get into more complex problems. The controller doesn't have the horsepower to solve, and we have IT security issues getting this data to the controller. So this data is some MIT data. This is chilled water tonnage. And if I'm gonna dispatch assets, I need to have a load prediction. And I'll give an example of why I need a load prediction and I need load forecasting, right? So the traditional methodology is regression. So I have this data set and it's load on the left and OA wet bulb on the x-axis here. And I plot this, and then I do in Excel, I make this equation. Then I get an R square value to 0.92, or even if I delete these data sets out here, or, I could get myself up to 0.97, and I feel really, really great about myself because my R squared is 0.97. But then I look at it and I'm saying, hey, wait a second here. This is misleading. Yes, I'm close to this line, But let's look at it in reality. Okay, 70-degree wet bulb. The equation is going to tell me that that is, what is that, 12,500 tons. Okay, but wait a second, the actual data could be 16,000 tons or 9,000 tons. I mean, that's such a big deviation. I can't make, this is worthless. This is completely worthless from a prediction standpoint. So we have to get better. So we have to get better. So that's where we've been playing around with machine learning for 5-6 years. We were excited. We went down into that trough of despair and said, hey, this stuff's worthless. And then we came out the other side and said, hey, load forecasting and macro fault detection is a really, really great application of machine learning. So we can feed in a lot more data into that model, and the tools are don't get intimidated if you haven't ever done it before. The tools are so simple to use now. I definitely it's pretty easy to use at this point. I'll leave it at that. So we have the data set here, same data set. I believe it's same, different data set, but same example. We have the predicted value in orange here, and you see the true value in blue, and the data is almost on top of each other. You're going to have some outliers that you can't really hit perfectly, but there's a whole different scoring methodology than R-squared. You quarantine a piece of the data, you build it on the remaining data set, you go back and score it on the quarantine data set. So that's a whole process. So I'm going to talk about why. So you might be asking, okay, why the heck are we predicting? Why do we care about this so much? I'll get into that in a second. But that definitely cannot reside within the controller. That's too hard, too complicated. This is just a fun example. Cooper Union, a real-time Sankey diagram. You know, I'm not going to build a real-time Sankey diagram in my BAS controller. It's going to bog it down. It's going to stop critical operations. But if that's something, you know, that's fun to do and you don't break anything, that's more for an analytics platform. Real-time MMV, right? So you have a lot of projects. Hey, dust off the old spreadsheet and let's see where we're at on that project from an MMV perspective. Hey, let's not do that anymore. Let's get our platforms to calculate real-time MMV. We can machine learn the historical load profile, score it, feel good about it on the so here's the historical electric load profile. Here's the actual load profile when we did an optimization project within the Robert Mondavi Institute of Wine here at UC Davis, right? So you can see the electricity is dropping off, and then this is real-time calculating the savings associated with that project. So it's a fault detection tool, and it's an MMV tool, macro fault detection, right? This isn't going to tell me why I'm no longer saving energy, but when I'm looking at a whole campus, I need macro tools on fault detection. I need micro, like what's my biggest offender, what's fallen off the optimization the most. We think machine learning is that tool. The micro tool, those can be rule-based, right? Is it an economizer? And I think at this point, everybody's pretty familiar with those rule-based fault detection. I'm going to jump into some projects here. Brookfield World Financial Center. This is some real case studies on some of this stuff. I got about 15 minutes left here before Q&A. So this is the Freedom Towers in the background here. This is a technically with the Winter Garden, a 5-building complex in Lower Manhattan. The chilled water plant that serves this complex is 5 floors below grade, so underneath the Hudson River in 250 Vesey. It's a 14-acre, 8 million square foot campus, and we were brought in to do optimization on the chiller plant there. The Con Ed network at the time of this project was really interested in demand reduction to get the nuclear facility offline. And then since then, their perspective has changed. They're more carbon focused, but at the time, I mean, we think that you can accomplish both, and we accomplished both at the same time on this project, but this project was really demand focused. So here's the profile in the year before we did the project, 2018, and then here's the demand profile in 2019. We took, the optimization project took 4.5 megawatts off the utility peak, and then the the M and V peak for the window that Con Ed was concerned with was 5 megawatts we reduced. So this is a 1983 plant. The customer's objective was to renew the asset, right? So we could have done, this is $11 million project, but we basically renewed the entire asset. It was, all the chillers were retubed, new VFDs, new compressors, basically brand new chillers, and a brand new control system. So don't get scared at this sticker price. We could have gotten a lot of the savings at a much lower cost. It depends on the objective of the facility. This facility wanted to maximize rebate, $4 million, and renew the asset, but also reduce carbon, reduce demand, and we accomplished that for this project. One of the notable kind of fun takeaways is we used a pipe flow model, which we had pipe flow open up an API on that model, and we were able to integrate BAS data into the pipe flow model, run it real time, and output pipe flow results into a screen. So I could, if I wanted to, I could throw a differential pressure transmitter right here, and it's going to grab that data from pipe flow and put that calculated value. And the model's calibrated, so it's a pretty accurate value at this point. And we have a lot of district thermal and customers, and they like this because if they have to add a building, it's not like, hey, call up ABC Engineering, let's dust off the old hydraulic model, let's rerun it. If it's constantly running, I'm going to know, hey, let's just do a pull down here, see when we peaked velocity on this pipeline. Yep, we got room. Our standards, 11 feet per second is our maximum velocity. We're good. We peaked at like 9 3 years ago. We got room. This is a fun screen for me because I'm a chiller nerd, but pretty boring for a lot of other people. But what I like about this screen is it has, at a glance, I can see all my machines and see if something's wrong instantaneously. Thrust bearing temperatures, stuff like that are gonna alert me. Whereas even the chiller panel doesn't really give me a preemptive on when the thrust bearing temperature is getting too high or motor winding temperature is getting too high. So it gives the operators one glance to just say, hey, everything looks good on a value that you don't really know that your winding temperature, your thrust bearing temperature is too high until there's catastrophic failure. So I'm going to jump into UC Davis here. You have the kind of obligatory KPI screens. The takeaway for the audience here is when you have these things turn yellow or orange, try not to have a static value. Try to have it be a dynamic value. Because 0.66 in the summer is good. 0.66 in the winter is not good. So let's make sure that scale, if we're looking at this and I'm looking for all green, let's make sure those scales are dynamic and make sure I go granular. I don't just want total plant, break it up into components. So I know if the total's bad, I can quickly see, okay, on the component level, which one's driving? And it's a lot quicker diagnostics. Here's a screen that shows chiller performance. So this is a real-time chiller performance map of the compressor showing the most recent instantaneous point. We plot the points. This is some complex fault detection, right? So we plot the AHRI MPLV points here against the manufacturer. So here's actual, here's design. So I'm going to know pretty quick if something's not running efficiently and I could do something about it. We'll do AHRI 550, 590 chiller performance tests, which are very expensive. You know, for electric chiller could be up to $20,000. For a steam turbine machine could be higher than that. And that's, you're getting one data point. Why not have your analytics platform run that calculation every 30 seconds, right? So we're running that heat mass balance from that AHRI 550, 590 test instantaneously, and I'm at a 2% heat mass balance. So I know that the instrumentation on my chiller is pretty good. And I have some other fault, approach fault detections here. Some rule-based fault detection, and make sure those are dynamic because approach temperature fault is a function of load. It shouldn't just be the peak value because the chiller is almost never running at peak, right? Okay, I'm going to give an example. I'm going to drive home now why I need to do, if I have more complicated desires or more complicated things that I want to accomplish, I need to have a load forecast. So I'm going to simplify the problem. I have a 1,000-ton-hour thermal storage system. Fictitious, nobody has a thermal storage system that small, right? But I have that, and I'm running here at 4 a.m. at 8,000 tons. So I'm the operator. I only got 1,000 ton hours, and I made it really small to exaggerate the example. When am I going to discharge that thing? So people think about this long and hard, but the answer is you have no idea. It's a trick question. You have no idea when you should discharge that thermal storage. So in this fictitious example that would never happen, the exact right time was 3 p.m., right? So if you would have done it at 8 a.m., you would not, if your objective, so that the optimization objective changes based on what your objective is. If you're in California CAISO, NISO, whatever your rate structures and objectives are, it's going to change. But in this fictitious example, I want to reduce my daily demand. So I should discharge the entire capacity right at 3 p.m. And if I didn't have a forecasted load profile, I would have never gotten that answer right. So here's UC Davis. They have very complex rate structure in this. They get WAPA power, which adds complexity on top of their CAISO. Yeah, just to take a step back, if we're not using, real rate data, we got to get there. I think that the days of blend rates are over. We got to really be rate sensitive. And this example kind of points out the rate sensitivity, right? So an inefficient plant's running at 0.9 kW per ton, and a really efficient plant's running at 0.6. You can see that that 0.9 at super cheap electric is 180 bucks, and the 0.6 at expensive electric is $420. So at UC Davis, my rate is driving things way more than my efficiency is. So we really have to be rate sensitive, right? So here's an example of where their rate is spiking, and they're actually electric use for kW is coinciding with that rate spike. And you can say that's really silly, and we can say that, but to their defense, to come up with this rate is basically PhD student, because it's complicated with WAPA, hydropower, how much hydro is coming off of so their instantaneous rates. So long story short, instantaneous rates really hard to predict there. So hard to figure out. So here's the dispatch, the optimal dispatch. So they're making chilled water obviously when the rate is lower. And then here's what that screen looks like. So like I said, at the end of the day, it's great that we have this PhD level optimization logic that figures out the exact time to turn and turn off the chillers. But I got to get an operator to do that to make the savings. So the simplicity of this screen is kind of beautiful, in my opinion. Obviously, I made the cake, so I love how it tastes. But if you see the data here, basically this is the current hour, and the data moves to the left. The cyan is future recommendations on which machines to run from an efficiency perspective and a thermal storage charge or discharge perspective. And this screenshot shows them running it pretty perfectly. There's a little bit of, it gives them a red box if it's a little off. There was a little bit of an issue here, but they've ran it perfect, and then they're gonna shut all the chillers off at the exact right time so the campus goes into discharge. We couldn't do that without a really nice load forecast and without a nice engagement for the operators to follow. And this has to be right. If this is wrong, the operators are gonna lose faith in it pretty quick, and we're done. So when you're dealing with facilities, folks, trust is key, and maintaining trust is key. So we have the unfun job of having to be right 95% of the time. Okay, jumping into some building examples. I think I got 5 minutes, and then I'll open it up to Q&A. So this is an older screen that we made in Siemens in Siemens Insight. We have a newer screen, but we're back to that Mondavi Institute of Wine. I mean, I like wine, so that's why I like talking about this building. But you can see there's a static reset here, and there's a temperature reset. And this is basically ASHRAE 36 code. We like Ash Rate 36. Some of the other platforms have it built in, like iView or ALC. And I think the movement is that the BAS vendors are going to build the logic into the controllers, but some of them are lagging and that logic's not there. And also, some of it we feel is actually wrong, and some of it's a little too complicated. So the static reset we think is great. We think the supply air temperature reset needs a little bit of improvement in the Ash Rate 36 because it doesn't really do a great balance between, well, one, I don't think it does a great balance even if it's all electric, but then let's say I complicate it and I have a cogen plant and my chilled water could be coming from steam production, and then my fan electricity is coming from the electrical production, and that might be grid because it's off the top. So if I'm starting to really focus on reducing carbon, it becomes a more complicated problem, and that's where we get this fun screen. So this fun screen's taking into, so this is simple, sorry. This is in the controller. This is doing a static reset based off of modified Ash Rate 36. And this is still using that logic. So that logic is within the controller. If I lose connectivity to the site, or if this site has, this is within the site, so they're using Pi, we're just built it for them. But this is going to determine that, this is going to do the more complicated math and do some fault detection, like leaky reheat here on this box, right? It's going to do some fault detection, but what this is going to do is it's optimizing to dollars or optimizing the carbon. In California, carbon and dollars are both synonymous, but in less advanced markets and grids, they're not synonymous. So you could pick, you could say, I want to optimize the carbon, I want to optimize the dollars, or I want to weight carbon and I want to weight dollars, right? This is a silly example, but I got a couple of seconds, so I'll go through it. So this is a Siemens building, and this is an example of something that doesn't require a lot of sophistication, but has a humongous impact. This is a lab controller. So in the Siemens, all control systems are different and they approach things in a different way. But a Siemens lab controller has canned applications, right? So what we've seen is, okay, there's actually I don't want to use glitch, but there's an opportunity for improvement within that canned application. And we're going to write external code that's going to kind of fix that or improve that application. So in this example, there's two opportunities here. The lab controller does not allow for a deadband on space temperature because they're like, oh, it's a lab, it's got to be really precise. But not all labs are created equal. So I have to basically break this controller to give it a space temperature deadband, because let's be honest, we're sipping and smelling wine here. I don't really care if it's 74 or 75, right? If I'm holding that precise of control, I'm definitely doing a lot of simultaneous heating and cooling. So we relax that. And then on the supplier side, this is it's going to track gen exhaust with supply air, right? But it's the application's ignoring the hood exhaust. So the standard, the EH&S folks or whatever you call that department, have worked with the engineering folks, and they've said, okay, 6 air changes is what we want, but you're actually doing 7.2 air changes. So what we're doing is we're saying, okay, we're going to calculate the actual air changes, stick it on the screen, and incorporate the lab exhaust. That's it. That's I ran through stuff. I could keep going for a couple hours, but I'm out of slides, so I'll turn it over to the Appalachian State guys for Q&A.
Thank you, Travis. That's great. It's exactly what we were looking for. Yeah, we have quite a few questions, and some of them are kind of overlap. So I'm going to group a few of them together for you. So the first is, from an overall standpoint of sustainability, how does all this technical work contribute to a decrease in the environmental impacts of these plants and buildings? And then another question was, what key strategies, you mentioned this, do you use to focus on energy and carbon?
Okay, yeah. So carbon is, so obviously if we're engaged at UC Davis and Stanford and Princeton, we've been involved in Princeton's carbon. Their 2020 plan, guess what year it is? 2020 now. So we're at the end of their plan. We started with them at the beginning. So I think there's a big uptick in carbon conversation, but I think we've been deep in the weeds for maybe 15 years on this stuff. So carbon is obviously, this stuff is super low hanging fruit from a carbon perspective. If we're, giving any of these examples, if we're dropping this site's total kWh almost 9 million on an annual basis, that's a substantial carbon reduction. So optimizing to play with the grid's cleanliness or dirtiness at time of day, I think, is the next frontier that the industry hasn't caught up to yet. But any obvious reduction in natural gas burning is going to significantly reduce carbon, oil burning, and electricity if your grid's not that clean. So all of these strategies are cost-effective ways of reducing carbon emissions. And they help pay to get to net zero, you're going to have to spend some capital, right? So do some of this easy stuff to help pay for the harder stuff, like hot water conversion and heat pumps and stuff like that.
Yeah, so you mentioned kind of the future being linked to time of day. So you also mentioned a lot of the ML technology has gotten through that chasm or trough of despair. What future ML technologies are you really paying attention to that might help you with this kind of getting dialing into the time of day?
I think that you got to be realistic on what it's going to do for us. Like, Amazon's way further ahead than we are. If you read enough about them, they also kind of, I'm going to say, they came to the same conclusion as us, but we definitely came to the same conclusion as them. But so what they're saying, and I think what the industry's saying, and I'm not a complete expert here. So what we're seeing is that pattern recognition is really where machine learning is awesome. Like, is there an uptick of spatula sales? Do we need to order more spatulas or get more production? If you go to, and that's obviously an Amazon example, or is data use, when is data use happening on their servers? And that's where but on the actual Amazon, on the package delivery and the machine code that's running the warehouse, that's locked down. You're not going to use machine learning to run the warehouse because two robots run into each other. So, it's going to create this whole Watson commercial where the computer's coming in and running the plant. We're very, very far away from that reality. Let's get our temperature sensors working right. Let's get our dampers working right. Let's get our flow meters there. I would say that there's a lot of low-hanging fruit. There's opportunity for machine learning. Some people, I think some people say, oh, I want to wait. I need to clean my place up first. If you put everything in series, you're never going to get there, right? So you got to put some stuff in parallel, but let's focus on cleaning up the broken stuff as a heavy focus if you have a lot of broken stuff. But do machine learning and data in a parallel because series, you're going to hit your carbon goal in 2100, and none of us are going to be here to see it.
Right. Was the 250 VESI CHW plant that you showed us using the Hudson River for cooling?
Oh yeah, sorry, that was using Hudson River for cooling. So I have a tight presentation here, but what that plant, it actually has a pump in, pump out, sensible thermal storage. So a competitor came in and said, hey, we want to put in a latent thermal storage or an ice plant. We said, hey, this is the only sensible storage plant in Manhattan, because why is there not sensible storage in Manhattan? We don't have the real estate, right? So the fact that this thing got put in 1983 is incredible. We're just not maximizing it. So that's another example of, we were $11 million, but the competitor was $20 million. So yes, so to answer the question, we're using Hudson River to reject heat there. No cooling towers in that plant.
Okay. Could you comment on considerations for determining if a chilled water reset is appropriate? Are there any drawbacks?
Ooh, that's an awesome question. So chilled water reset's one of those really fun ones where you guys, I'm in Denver now, but I grew up in Florida, and I worked in Manhattan, did a lot of work on the East Coast. We're all aware of humidity, right? So humidity's almost got to be we've seen a chilled water reset implemented in a humid region with a neglect to humidity and dehumidification, right? So you have to incorporate dehumidification into that chilled water reset strategy. but also just be pragmatic, right? If my outside air, or my average space temperature, or my dew point is 40 degrees, why the heck am I sending out 42-degree chilled water? It's impossible for me to pull moisture. It's impossible for me to drop the air below the dew point. So it's a very pragmatic approach. But so that's the rule-based component of it. Hey, if I'm humid, I need to be colder. The more challenging component to it is what's that balance between pumping energy. I'm going to increase the log mean temperature differential on my heat exchanger at a high up on my evaporator. That's going to reduce the approach temperature on the evap, which is going to reduce the lift on the machine. That there's a savings component to that. So that one is actually, the optimization gets pretty complicated on chilled water reset.
Gotcha. So we have several questions that have to do with platforms. So I'm going to combine these, and
Sure.
just let me know if you want me to reread.
I'll try to keep my biases out of this.
Okay. Do you have in-house controls expertise for various controls programming software, for example, Trains Rover or Snyder's Workplace Tech? Or do you typically work with control vendors to optimize retune systems? And they said, great presentation, thanks. And okay. Then the other is on your comment about spreadsheets for a university looking to upgrade from homegrown spreadsheets. Can you suggest platforms that satisfy basic data analytic needs as well as serve as a more advanced platform that are still user friendly? And then you also wanted to know what platform is used by UC Davis.
Okay, great. Great questions. Okay, so we hit on one that's like a pet peeve and near and dear to my heart. So I'm talking to most of the universities here, right?
Yeah.
Okay, so a huge pet peeve of mine is, working at Princeton. Like, I really see Princeton. I've worked across all the board, and it was one of my first really big customers. So maybe that's why I have a bias, but I really love what they do there. And the thing that I really learned from them was they're bringing the controls in-house. And I've just seen such great things to that. Why continually invest externally where you're never going to get a return on that money, right? Whereas if you're doing the work and you're investing internally, you're going to maintain that knowledge into perpetuity. And let's be honest, universities are a great place to work right now. Benefits, job security, well, hopefully. But yes, so it's a great place to work. You can attract this talent. Definitely, if you don't have a program to bring your techs in-house, please start it. That is where everybody in the front is moving. So to answer the question, though, we started off as an engineering firm, and we learned that controls is pretty much everything. So we started hiring techs. We got really into controls. So we have in-house controls techs. Our objective is to have a tech for pretty much every dominant platform. Because so when we don't have the controls tech, we prefer to work with the site expert in that controls and have he or she do the programming, because they have a vested interest in it really working well. The backup to that is a preferred vendor. We work with them, but there's always a loss in translation there. My guys have done it 20 times, and we just know we work together. The communication's there. So when we work with the external vendor, which we have to do a lot, PLC systems, DCS or Delta V, we don't have any of that in-house, so we work with a vendor. There's a getting to know each other. There's a dance. There's a, and then there's a loss. Oh, okay, I kind of see what you're doing. No, this is really critical that you exactly see what I'm doing, because an extra 20 seconds on the dwell timer is going to change the entire program, right? So to answer the question, we're agnostic to platform. From a controls perspective, use what you have. We bring the vendors in-house. We prefer to work with our guys. Second to that, your guys. Third, your vendor. And then the platform that Davis uses for the BAS is Siemens. The plant is PLCs, Allen Bradley with the Wonderware front end. And then the historian/analytics platform, they're like us. They like a lot of tools. Think about it like no, don't pick one tool. You need a bunch of different tools in your toolbox. So SkySpark they use SkySpark, we use SkySpark, but SkySpark has a limited functionality. It is great for rule-based fault detection. Pi, OSI Pi is an awesome tool, great historian to make this screen, to make this screen, to make this screen. That's an intern for 15 minutes. So really, really user-friendly interface with Pi Vision there. I don't want to leave any platforms out, but to be overarching, let me give you a recommendation on the platform. Something that you can play with yourself. Pi has a lot of, there's a question about Excel. Pi has a lot of Excel linking tools. So like I can make a report on this data and have it automatically run on a monthly basis. So automate, if you're not there, automate your reporting. And even if it ends up in an Excel, because Excel is widely used, that's fine. But you use some standardized tool for the automation of that. I know I'm forgetting platform. So make sure that you're able to use the tool in-house. You don't want to be in a position where you have to call the vendor every time you want to like make a change on the tool, right? So Pi, I'm drawing a blank on some of the other platforms, but yeah. So UC Davis uses SkySpark Pi. This is a UC Davis Pi screen. Yeah. Any other questions, I guess?
Yeah, no, that's great.
Iconics. Iconics is another good platform that is good. Sorry.
That's okay. So yeah, we have time for one more question. And yeah, there are others from outside higher ed, local government, and
yeah, I don't want to leave any of those out. There's a lot of great tools out there. I would say you're going to need more than one tool to get the job done.
Yeah. So we had one last question I want to ask that came in. This is all exciting stuff for big plants, large building complexes. Can any of these technologies translate to households or even in dense housing or apartment complexes? Is there any movement in sharing HVAC capabilities?
Yeah, I think that's a fun question. I mean, I'm really focused on like the Merck Pharmaceutical 100,000 ton chilled water plant. And obviously from a business standpoint, we're there because there's a large barrier to entry. I definitely think if from a business perspective, I would say if I was going to penetrate the housing, it would be Nest thermostat. I need something that can scale quickly if I want to make a carbon impact, right? So Nest thermostat, I think is a cool example. Once again, I'm using, there's probably other brands that are doing the same thing. But from a house perspective, I think it's really cool, what Tesla's done and the ability. I think it's gonna come out that Tesla makes cars and they have the solar and they have the battery. They're gonna come out that they're gonna be the biggest demand aggregate. Like if they send you a text and say, hey, do you mind if I discharge your car into the grid right now? I'll reduce your lease payment by this amount or something. So I think that's where things are going to get really cool on that side. And then you guys have a lot of charging stations, and then there's companies that are in this space, but that's where things are going to get cool on the house side, I think. And it's already there, So maybe thermal storage makes sense on a little tiny house level, but heat pumps definitely make sense on a house level. But the controls are really, really simple. I would say package controls, like taking it up to the high school level, like I would almost say do an air-cooled chiller on a high school level, because once you start making it too complicated, we don't do high schools, but I've seen them. They have this, theoretically a water-cooled chilled water system is more efficient, but the guy doesn't understand it and he runs it at 85-degree condenser water all the time. And now this thing's consuming more energy. I've got chemical treatment. I've got Legionella. I've spent way more on this system. I'm consuming more carbon. Keep it simple, stupid, right? Put an air-cooled chiller. It's all package controls. Let that that janitor, stick to doing some other, fixing the broken damper in the room. Like give the guy, you gave him a spaceship to run here. So keep on the high school side, the simpler, keep it simple, stupid. I think you're going to get better results.
Yeah, Joe Seabrook used to always say that. Travis, really appreciate your time. This is great. Wish we could, spend, more time, but everybody's got to, get back to their work task lists, but this is exactly what we were looking for. We really appreciate the fact that you have all this expertise and you're sharing it with us. And I know a lot of people will probably be interested in getting in touch with with you in the future. So again, thanks so much for coming. This has been great.
Thanks for having me.
So just want to remind everybody that we have 2 webinars remaining in the series on October the 15th, Sustainability and Energy Initiatives in Local Government, and on October the 22nd, Principles of Integrated Project Delivery. So thank you for attending today's webinar. I hope you enjoyed it, and please try and attend the ones in the future. Bye, everybody.